Oftentimes when we're describing soils, we describe them as a homogeneous mass, and then we can look at the processes in that homogeneous mass. That, unfortunately, is a dramatic simplification over reality. And here we have a picture I took at the Hanford site in Washington State, resulting from a series of large-scale inundations. And so these are the Hanford layers. Very heterogeneous, very layered, and you can even see micro-layering within layers. So you have these kind of dark sand areas with micro-layering. What is the impact of such layering on our overall flow processes? And let's just take a quick look just to kind of humble ourselves a little bit and understand what the impacts of such capillary changes are. So we have these layers, coarser and finer, and what happens when you put flow onto that. This is an experiment I ran back in 1990, and it's about a 2-meter wide chamber. It has a coarse wedge in it and then fine sand all around it. And I've put blue dye down in traces. And what you can see, it's raining uniformly over the system. The water goes down, hits the capillary barrier, and the thing is that even though the light is brighter, that coarse sand is much drier. So the fine sand holds the water, and it makes essentially high conductivity above that layer, and it just routes the water right over the coarse layer. So even though this is all above the water table, that coarse layer takes on the feature of being impermeable. And so so the fine material holding onto the water has higher permeability, directing all the flow over that. That's called a capillary barrier. And that can be quite useful if you wanted to put waste material under this. That could create a cap that would be resistant over over geologic timescales. So there's a lot of appeal to that. We could also, once we kind of get excited and think in terms of our engineering ideas, we can optimize the shape of that capillary barrier. We know that at the peak of the cap where the rain is hitting, there's very little flow, whereas downstream it accumulates flow. Therefore, the slope of that capillary barrier should be proportional to the amount of water that it's diverting, which actually means it should be a parabola. And so this is a numerical simulation of 2 stacked parabolic capillary barriers showing very, very good divergence, because that is actually the optimal shape for diverting water using a capillary interface. So we can use our engineering skills with this. And we can also then say, well, what about in a natural setting? Well, at the Hanford location, as it turns out, where the United States refined most of its plutonium, they had very high salinity solutions to pull out the plutonium. And so 5 molar, in this case, sodium nitrate. And what we see when we put this 5 molar sodium nitrate on the situation is that it does indeed follow that's the lower image is an actual infiltration. It follows these microbeds. But the interesting thing is that because it's so salty, it's actually pulling water out of the resident soil by osmotic forces, which then deposits the water into the moving water, or saline solution we should say, and it actually drives lateral flow. And over the course of 50 years, this can drive lateral flow hundreds of meters. And so we see at the Hanford site that these contaminants, when they hit this layered site, had a flow behavior very unexpected and very different than we would have seen had this been a homogeneous soil. And also quite different than we would have seen had it been a non-saline solution. So the combination in this case of salinity and layering had great impact. The point is that when we look at flow through real soils, we have to understand the particular character of those soils. Is it layered? Is it are there macropores involved? And then what are the impacts, and how can we leverage that understanding to make better predictions of the final fate of, be it water or saline solutions or contaminants?